Our next section is on acceleration. We're going to be able to talk about the relationship between a particle's average acceleration, its change in velocity, and the time interval for that change. Also going to look at graphs of velocity versus time and determine the instantaneous acceleration for a certain time and the average acceleration between those two different times. When a particle's velocity changes, the particle, we say it undergoes acceleration. So our average velocity is denoted as the difference between our two different velocities divided by the change in time. So the change in velocity divided by change in time, or delta V over delta T, is our average acceleration. Instantaneous acceleration is the derivative of velocity. And this is a limit equation and a formula. And this is a little bit more advanced than I would prefer to have in this class. But anyway, this is saying that acceleration is the derivative of velocity, and this is the derivative with respect to time of x over derivative of respect to time, and we get this d squared x over dt squared. That's a little bit less important, but the acceleration, we express acceleration in meters per second squared, and the acceleration due to gravity is, we say, is 1g, and that's equivalent to 9.8 meters per second squared. This is very important. The sign of acceleration indicates the direction, not whether the speed is increasing or decreasing. So if a car has an initial velocity of negative 25 meters per second, if we're looking at that on a number line, it's moving to the left. And if it is braked to a stop in 5 seconds, its average velocity is still positive, even though it's slowing down. Or excuse me, its average acceleration is still positive, even though it's slowing down. Acceleration is positive even though the car's speed has decreased. All right, we're going to look at an example in physics now with finding the derivative and looking at acceleration. So we have this particle's position on the x-axis, and they tell us the position function is x is 4 minus 24t plus t cubed, with x in meters and t in seconds. Because the position depends on the time, the particle has to be moving. We want to find the particle's velocity function and acceleration function, a of t. So in order to do this, we're going to find the derivative of displacement. So this is our position. This is our position function. So we're going to find the derivative of that, and that equals our velocity function. So this is our new velocity function once we find the derivative of this given function of the particle's position. And you might hear me say position and displacement a bit interchangeably at times. I will do the best I can to be as specific as possible. But sometimes I might use those interchangeably. If we take the second derivative of the position function, that is the same thing as the derivative of velocity, which equals acceleration. So if we take the derivative of velocity, that's just 2 times 3 minus 1 on the exponent. That gives us 6t. Part B says, is there ever a time where velocity is equal to 0? And so we're going to set velocity equal to 0. This is the function for velocity that was calculated from part A. And we just set that equal to 0. So 0 is negative 27 plus 3t squared. And then we solve for t. And this is, whenever we do a square root of something, we get a plus and a minus answer. I think a lot of people usually just think there's one answer, but we technically get two answers. We get a positive and a negative answer. So it might not quite make sense when time is negative 3 seconds. That seems a little bit strange, But in physics, we can measure time in terms of negative seconds. It's not that common, but sometimes we do. Part C says describe the particle's motion for when time is greater than or equal to zero. So when time is equal to zero, we can find its position, we can find its velocity, and we can find its acceleration. So if we plug in zero for time for our position function, this we can write x of t. So it does say x there, but we can actually write it like x of t, like that, for position. And we can do the same thing for velocity and acceleration as well. And so if we plug in zero for t, we get at 0 seconds, the position is 4 meters. If we do the same for our velocity function, we get negative 27 meters per second when time is zero. And when time is zero for acceleration, it is not accelerating at all. It's going 0 meters per second squared. All right. Now we want to figure out what's happening beyond that. So we have these starting values of when it is at zero, but we want to find out next what's happening in terms of the particle's motion when it's greater than zero. So I just picked a number 3. So when time is equal to 3, we're going to plug in 3 for t for our position function, for our velocity function, and our acceleration function. So when we plug in 3 for t for our position function, we get negative 50 meters. When we plug in 3 for velocity, we get 0 meters per second. And when we plug in 3 for acceleration, we get 18 meters per second squared. And again, all I've done is I've just used the function that they gave us for position, plugged in 3, the velocity function, which we calculated just a moment ago, plugged in 3, and the acceleration function, which we found just a moment ago, and plugged in 3. So we got 0 or negative 50 for position, 0 for velocity, and 18 for acceleration. And here's what those values are. All right, so now we have to describe in words what's happening with the particle's motion. So from 0 to 3 seconds, let's see what's happening here. Displacement is getting more negative from 0 to 3 seconds. From 0 to 3 seconds, velocity is increasing. So it's starting at negative 27. It's starting at a negative value, but it's ending up being at 0. So even though the velocity is at 0, it's still increasing when we check from 0 seconds to 3 seconds. And the acceleration is also increasing. So we increase from 0 seconds to 3 seconds. Our acceleration goes up by 18. All right, and here is the workbook assignment that is associated with the acceleration lesson just covered.